Okay. The topic of my presentation is a theoretical approach to calculate the photofield emission current of metals and semiconductor. These are the objective of my presentation. First will be the introduction, and second will be the photofield emission current calculation result and conclusion. Photofield emission. Photofield emission is a technique in which a metal is irradiated by an incident laser radiation of photon energy h cross omega. Photon energy is usually less than the work function phi of the metal. The incident radiation photoexcites the electrons to states which lies between the Fermi level and the vacuum level. Hence, these electrons are confined within the metal surface. A strong static electric field approximately equal to 10 to the power 11 volt per meter when applied to the surface of the metal causes the photo-excited electron to tunnel through the surface potential barrier into the vacuum region. These electrons, which are now emitted into the vacuum region, constitute the measurable photofield emission current PFEC. The incident radiation causes the transition of the element from the initial state I to the final state F, and the matrix element of the transition can be written as this one, M equal to F AP to P dot Fi. This is the formulation of the photofield. The formulation used for calculation of PFEC is given by this one. In the above equation, F E minus H cross W is the Fermi direct distribution function. D omega is the quantum mechanical transmission probability, and the energy of the photo-excited electron is given by this equation. This one. W is the normal component of energy, E kinetic energy. This electron will travel across the surface potential, which is deformed by the applied electrostatic field and the image potential barrier. The transition probability is given by dW. This equation is used to calculate the photofield emission current. This is the formulation of initial state wave function by using Green's function method. The crystal potential of delta potential, which represents the Cronin-Penny potential, is periodic with the periodicity of the lattice as shown in figure 1, applicable to the strongly bonded metals like the Benz metal. In this method, Schrödinger equation will be solved to obtain the solution in terms of Green function. Cronin-Penny model has been used in connection with surface electronic state by several authors. Scutts and Ashcroft have calculated numerically the photo yield by using the modified form of the Cronin-Penny model. Steliska had performed a detailed calculation of the surface states using the Cronin-Penny model, both of the semi-infinite and finite crystal model. Eldip et al. Has also applied Cronin-Penny model to one-dimensional crystal. They had calculated only the electronic energy band for the mono and polyatomic crystal and compared the data with one of the occupied using LCAO method. This is the equation which we are using to find the initial and final states of the incident wave. I'll just skip this slide. These are the initial state function. The initial state function can be written in this form, where phi z is the complex conjugate and phi star z is the complex conjugate of phi z. R is the reflection coefficient, and T is the transmission coefficient across the boundary plane, and x naught square equal and this equation, and V naught the potential at the surface which an electron encounter while transmitting through the boundary surface. Matching the wave function and its derivative at z equal to 0 give the value of coefficient R and T. And again, we are solving this equation. finally, we came to the final initial state wave and final state wave function equation. This equation 20 and 21 are the final initial state wave and final state of wave function of the equation. Now we are going to calculate the photo field emission current of metal and semiconductor by using green function method. For this calculation, we are using gallium nitride, which is a semiconductor. The variation of photo field electric current for gallium nitride as a function of photon energy H cross omega is applied applied static energy field F and initial state energy EI at the surface and bulk region. To calculate photo field emission current, green function method is used, in which the basic function used is calculated by the projection operator method of grip theory. The parameter used for calculation of photo field emission current using green function method are surface with D equal to 4.71 to 6 Armstrong, initial state energy EI equal to 7.6833 electron volt, potential barrier height at the surface V naught equal to 1.13.503 electron volt, work function phi equal to 3.5 electron volt, Fermi energy EF equal to 10.08 electron volt, and the scattering factor alpha equal to 0.35. Now here are the results of the results. The following graph, which I will show it later, is the result which we have calculated. The following graph shows the calculated result of photo field emission current in gallium nitride using Green's function method. Figure 2 is photo field emission currents against photo energy H cross omega. Figure 3 is photo field electric current against applied electric field for two different values of photon energy, and figure 4 is photo field emission current against initial state energy for two different values of photon energies. Figure 5 is photo field emission current against initial state energy for two different values of the photon energies. Here is the figure 1. Figure 1 is a plot of variation of photo field emission current against photon energy H cross omega in gallium nitride using Green's function method. The angle of incident photon radiation is theta I equal to 45 degrees. In figure 2, we have plotted the calculated result of photo field emission current as a function of photon energy. Here we have chosen the initial state energy EI equal to 1 electron volt below Fermi level, EF equal to 0.0, and the angle of incident photon radiation is theta I equal to 45 degrees. And from the plot, we find that the photo field emission current PFEC increases as photon energy increases, but it became maximum at about photon energy 3.687 electron volt. With further increase in photon energy, photo field emission current decreases and it becomes minimum at H cross omega approximately equal to 4.25 electron volt. The second graph is a plot of photo field emission current against applied electric field for two different values of photon energy in gallium arsenide using Green function method. The angle of incident photon of radiation is theta I equal to 45 degrees. In figure 3, we have plotted the result of calculated photo field emission current as a function of the applied electric field F for two different values of photon energy H cross omega equal to 3.687 electron volt M, 4.013 electron volt respectively. From this plot, we find that the value of applied electric field F increases photo field emission current decreases from a high value towards minimum in an exponential manner for both the values of photon energy. The exponential decrease in photo field emission current is due to the presence of exponential term. We also find from this plot that the value of photo field emission current maximum for low photon H cross omega equal to 3.687 electron volt, and it will be minimum for large photon energy H cross omega equal to 4.013 electron volt. However, the variation of photo field emission current for both the values of photon energy are similar in nature. In In figure 4, we have also plotted the calculated result of photofield emission current as a function of initial state wave EI for two different values of photon energy H cross omega equal to 3.68 electron volt and 4.013 electron volt respectively. From the plot, we find that photofield emission current for photon energy S cross omega equal to 3.687 electron volt shows a minimum peak at initial state energy EI equal to 3.00 electron volt before the Fermi level. We have also plotted the photofield emission current for photon energy S cross omega 4.013 electron volt as shown in figure 4. This is due to the fact that photofield emission current is inversely proportional to the cube of frequency of incident photon radiation, which is given in the earlier equation. In both the cases, we also find that beyond this peak, photofield emission current decreases exponentially and decreases of initial state energy. The exponential decrease in photofield emission energy is due to the presence of exponential charm. In figure 5, we have plotted the calculated result of photofield emission current as a function of the applied electric field F for three different values of photon energies. H cross omega equal to H cross omega for we have chosen the initial state EI equal to 1 electron volt below Fermi level, EF equal to 0.0. From the plot, we have seen that the value of applied electric field when increases to photofield emission current decreases from a high value towards minimum in an exponential manner for all the three different values of photon energy. This is the reason that an exponential term is present in transition probability formula. From this plot, we have also seen that the value of PF is C minimum for low photon energy S cross omega equal to 2.8708 electron volt and minimum for high photon energy S cross omega equal to 4.013 electron volt. This is true that photofield emission current is inversely proportional to the cube of the frequency of incident photon radiation. However, the variation of photofield emission current in all the cases of three different values of photon energy are similar in nature. And this is the conclusion. For calculating photofield emission current using green function method, the basic function is were calculated by the projection operator method of group theory, which is calculated by Thapa and Das. Photofield emission current against the applied electric field decreases exponentially with the decrease in applied field. This is because of the exponential term is involved in the formula for transition probability d omega dw. These are the reference which we have taken. And these are the compiler used for calculating the initial and final state wave of the state wave function. And thank you. Is there any question?
Well, thank you for your presentation.